All right, so today we're going to work on some logarithmic equations. So we already did number 5, so we're going to be looking at questions like 6, 7, and 8. So the big idea for logarithmic equations is, first of all, you can identify them because they have a log. So you can see this 7 and 8 clearly have a log. 6 also has a log. Remember that when we have ln, that's a natural log. It is still a log. And so kind of the same rules apply. And so the rules for logarithmic equations are as follows. So we kind of have two different types of logarithmic equations, actually. If you have log equals a number, you're going to want to do the exponential switch. And so we'll talk about that. And so all of these are actually log equals number here. But if we have log equals log, we're going to want to just drop the log. So we are only allowed to do that if it is log equals log, and they have the same base. So we'll see some of that later. So most of what we're going to be doing, these first three, are the first one. But for both of those, you have to check extraneous on these ones. Now, check extraneous on these is actually pretty simple. You just have to plug it in and make sure there are no negatives. Let me give it some more space. No negatives in original logs. So let's start off here with number 6. So on number 6, we're going to switch this to the exponential form here. And so remember that ln is a log base e. And so when I switch to exponential form, it's going to be e, and then get the new partner is 1 equals 2 plus x. And so we could subtract the 2 over, and x just equals e minus 2. You could leave your answer like that. I think is fine. If you wanted to use the calculator for a decimal approximation, that's fine too. And so you can also say x is about 0.7182. I guess I should have gone 83 there if I'm going to round it up. All right, so we do need to check this now for extraneous solutions. And if you kind of look back here, you can really just do this in your head, especially on this one. So 2 plus x. And so if we kind of plug in our number here, 0.718, the decimal is probably easier to see. You can see that makes it positive inside of the logarithm. 2 plus some little positive decimal, of course, will be positive. And so that is not an extraneous solution. So that's all you have to do for the extraneous check. Just make sure it doesn't make the inside of the log negative, the original log. Okay, so now let's switch over to number 7 here. So we're going to do an exponential switch again because we have log equals number. So I'll go 3 to the power, that's my base is 3 to the power of 3 equals 11 minus x. And so now we'll go ahead and solve this. So 3 to the third power, of course, not 9, but rather 27 equals 11 minus x. And then we'll subtract the 11 over. Negative x equals 16, and then we'll divide by negative 1, and x equals negative 16. Now, let's check it for extraneous. Some of you may be thinking, oh, that's negative, that must be extraneous. But if you actually plug it in here, it's 11 minus negative 16. That's actually a positive because it's a minus to plus thing. So that means this answer actually is correct. Although the x value is negative, when we actually plug it in, it's a positive inside that original logarithm. All right, next up here, we'll do number 8. So here we have another log equals number, so we'll do the exponential switch. So my base is 100 to the power of 1/2 equals x squared minus x minus 2. Now 100 to the 1/2, remember, is really the square root of 100. It's not times 1/2, it's to the 1/2 power. So the square root of 100, of course, is 10. Now, the right side here looks like we might want to factor it, but remember, we don't want to factor equal to 10, so I'm going to move this 10 over. And so we get 0 equals x squared minus x minus 12. So that's what I'm going to be factoring. It looks like a pretty simple factor here, x minus 4, x plus 3. So we get x equals 4, x equals negative 3. Now we do need to check those for extraneous solutions, and so I'm going to plug them back into the original log, right, the inside of the log right there to make sure it comes out positive. And so if I do 4 squared minus 4 minus 2, that's 16 minus 6, that comes out to 10, which is certainly positive, so that one's good. And then negative 3 squared minus negative 3 minus 2. Let's see, that's 9 plus 3 minus 2. That is also 10. So actually, these are both correct. A lot of times when you have two solutions like this, one of them will be extraneous. But in this case, it's not. In this case, they are both legitimate. And so they're good to go. All right, next up here, number 9. On this one, you can actually see we have logs on both sides. So on this one, we are going to do the drop the logs trick from back here. But I need to condense these logs first, so I need to get it to 1 log equals 1 log. And so, of course, if we have logs that are adding separately, that means we're going to multiply them together. And so that's going to become x squared plus x, and I'm going to distribute that x in there. Oh, that's base 5, okay. Now, I think you can see the logic here as to why we can drop the logs on this one, because obviously log base 5 is the same as log base 5, so we just need the insides to be the same. So I just need x squared plus x equals 20. So then I'm going to get one side to 0 and factor. So I get x plus 5 and x minus 4 equals 0, which means that x equals negative 4 and x equals, negative 5, excuse me. And x equals 4. Now, we got to check these for extraneous. And so if I plug in, and this one I'm going back to the original, not my first step, but the original logs. And you can clearly see if I plug in negative 5, that's going to make a negative inside a log. Either one you plug it into, and 4 is A-OK. So that one, we got 1 extraneous on that one. All right, next up here we have number 10. Now this one, I again have 2 separate logs, and they are subtracting, so I'm going to condense them by dividing. So this is going to be x over x minus 3. All right, and so now what we're going to do is, this just equals 1. Okay, so this is not log equals log anymore. This is log equals number. And so I cannot just drop the logs. I have to do the exponential switch. So just remember that this log is really base 10. So when I do my exponential switch, it is 10 to the power of 1 equals x over x minus 3. Now in this case, I would multiply the x minus 3 over to the other side. I would go ahead and distribute that 10. So I get 10x minus 30 equals x. I would subtract 10x over to this side. I get negative 30 equals negative 9x. Divide by negative 9. And I would just reduce that and say x equals 10 over 3. If you like 3.3 repeating, that's fine too. And if we plug that back into the original logs, positive 10 over 3 there is fine. 3.3 minus 3 is positive as well, so we did check that for extraneous, and it is still good. All right, now we're going to be getting back into our compound interest formulas. And so it says Nancy wants to borrow $4,000 from a loan company, charges 9.75% interest, compounded semi-annually. How long until she owes $5,000? So in this case, now we're using these formulas again, but now we're solving for t. And so it sounds like we're initially borrowing $4,000, and then we end up owing $5,000. So that's our P and our A. The A is always going to be bigger. And then we have our N is 2 here for the semi-annually. We have our interest rate there is 0.0975. Okay, so let's set it up here. So we got 5,000 equals 4,000 times 1 plus 0.0975 over 2 to the power of 2t. All right, so the t is the unknown there. It's in the exponent, so I'm going to have to use logs. I first need to divide by 4,000. So we're going to isolate our base. And so we go 5 over 4. You can use 1.25 if you like. And then I'm going to we'll leave this like this, 0.0975 over 2t. Okay, to the power of 2. Oh, no. It's going to be over 2 there. To the power of 2t. And now that I've isolated the base here, I'm going to do the exponential, or so we do a log switch. So this whole thing is the base. And so you could do a decimal for that. I like to just leave it all like that and just know that that's going to be my base here. 1 plus 0.0975 over 2. And so log base that, the new partner is going to be 5 over 4, and that's going to be equal to 2t. So now I can do my change of base formula. So I'll go up here and do that. So now I'm going to type this in the calculator. So it's going to be log of 5 over 4 over log of 1 plus 0.0975 over 2 equals 2t. So I'll type that in the calculator now. So I get that 4.68, 8 we'll call it, equals 2t, and so I'll just divide that by 2. And that comes out to 2.34. Remember in this formula that time is always in years, so it takes 2.34 years for that to grow that much. All right, number 12 here, again, we are looking for t, because it says how long will it take. And I think it's pretty clear here that r is 0.05. We know that n is 12 because it is compounded monthly. The tough part here is a and p, though. And what we're going to do that based on is how long does it take for an account to double. So account to double, well, there's actually several different ones I could use. So if you want to pause it and kind of see what you think a and p could be, go ahead. So here we go. Here's one thing we could do. We can make p $100 and a $200. That does double. But another thing we could do is we could make p, I don't know, $50 and make a $100. That would be doubling as well. We can make p x and we can make a 2x. All of those would actually come out the same. And then there's one more. So this is like or here. There's one more here that I really like to use. Whenever this happens with me, I just make p equal $1. And then I make a equal whatever it is, double that or triple it. So any one of those that you would like to use, I'm going to go ahead and use the $1 and the $2. They all come out to the same answer. And as we set this up, I think you're going to see why. So I'm going to set it up here. So 2 equals 1 times 1 plus 0.05 over 12 to the power of 12t. And the first step is to divide that 1 over to the other side. Now, obviously, when I divide that over, it's just going to be gone. So I'm just actually going to scribble it out. So that's why it's nice to use 1. You can see that if I use the 100 and the 200, I would end up with the same as my second step, but I'm just kind of saving a step here. So now I'm ready for my log switch. So it's going to be log base 1 plus 0.05 over 12 of 2 equals 12t. In my calculator, I'm going to do the change of base. So log 2 over log of 1 plus 0.05 divided by 12 equals 12t. So we have log 2 divided by log 1 plus 0.05 divided by 12. And so that's 166.7 equals 12t. Just divide that by 12. And we get t equals 13.89 years. All right, next up, we have the man invests $6,500 in an account that pays 6% per year. Now we're compounding continuously. So remember, that just means we're using a PERT because there's no n value. And so we know he's going to end up with 8,000. He's going to start off with 6,500. And it's going to be e to the power of 0.06 times t. We're looking for time now. So now we're going to divide by 6,500. I'm just going to cross off these zeros and leave it as 80 over 65. So we have 80 over 65 equals e to the 0.06t. So now I'm ready to use my exponential switch. Now this is a base e, which I really like because when we switch it to a log, it's just going to be a natural log. So ln 80 over 65 equals 0.06t. So these are actually easier, I think, because you don't need to use change of base. So you can just use a natural log. I'm just going to divide the 0.06 right now and type that all in the calculator in one step. And make sure I close the parentheses after the 65. So we'll go ln of 80 over 65 divided by 0.06. And that comes out to t equals 3.46 years. All right, next one here, number 14. So on this one, we have our, let's see, a and our p there. And compounded continuously means we're going to use p times e to the rt. We actually don't know r here, so I'm going to leave that as a variable. And t here, 6 months, remember, is half of a year. So I'm going to do 0.5 there. So r times 0.5. Okay, so I'm going to divide the 2,000 over. Got to isolate that base first. I already know I'm going to use a natural log here. So I say 2012 divided by 2,000 equals e to the 0.5r. And now I'm going to do my natural log of 2012, since this is a base e, equals 0.5r, so divide by 0.5. And we're going to type all that in the calculator. All right. And I get that r equals 0.01196, which I'm going to convert that to a percent and say 1.196%. All right, next up here, we're going to write some exponential functions. And so I'm going to write it in two forms here. And so we'll look at the two forms and see what's going on there. So the first form here, y equals a times b to the power of x. So this one, we've actually already done this before. And so what we're going to do here is I actually know that f of 0 on both of these is going to be a. So that's a little shortcut you can do. So I know on this one, a is going to equal 3. That's going to work for both of them, actually. And so the next thing I need to figure out then is what's the other value. So in this case, what's b? So I'm going to say, well, I know that y equals 3 times b to the power of x. I'm going to plug in the other point. So we get 75 equals 3 times b to the power of 2. So I'm going to divide the 3 over. And so 25 equals b squared. We'll square root it, and b equals 5. It's really plus or minus 5. But because it's the base of an exponential equation, we want it to be positive. So for this one, I'm going to say y equals 3 times 5 to the power of x. Now I'm going to do the same or similar thing with the other one. So I still know that a is 3. That's the initial value. And now I got to figure out what k is. So I'm still going to use the other point and figure out what k is here. And so 25 equals e to the 3k. Now on this one, instead of our variable being the base, it's actually in the exponent, which means I need to use a log. And so this is a e base, so I'm going to use a natural log. So ln of 25 equals 3k. And so ln of 25 over 3 equals k. And so you can just leave it like that. You can also get a decimal for this. So ln of 25 divided by 3. Is 1.073, we'll call it. So that one, so you can see the difference here. If our variable is the base, like on this one, we use a root. If our variable is in the exponent, we have to use a log. So let's do the same thing for number 16. If you want to pause it and try it on your own, you can certainly do so. All right, so on this one, I know a is 48. And so I know I can do use the other point and say 3 equals 48 times b to the power of 4. And so 3 divided by 48, that reduces to 1 over 16 equals b to the 4th. So if I do the 4th root to that, or I raise it to the 1/4 power, then that comes out to b equals 1/2. And so I could say y equals 48 times 1/2 to the power of x. Now for the other form, I know that a is still 48. Let me do this in another color here. So then we have 3 equals, using the other point now, 3 equals 48 times e to the power of 4k. And so I know then again 1 over 16 equals e to the 4k. And then we will do our exponential or log switch here. So ln of 1 over 16 equals 4k, and then divide that by 4. And if we want a decimal approximation of this, do that. Ln of 1 over 16 divided by 4, it was negative 0.6931. So there is our k value there, and we have our a value there, so you could set up the formula if you like. This one did come out negative. That actually makes sense because this is exponential decay. And so when it's exponential decay in this form, you'll see it's less than 1 in the base. In this form, you're actually going to see the exponent is negative because that kind of flips it so that it's decay.